Hello, friends. So today we're going to be learning lesson 11 from Unit 2, which is fixing a function to make it differentiable. So in our previous lesson, we learned that a function is differentiable if the derivative exists. In this lesson, we're going to really be focusing on finding a missing value from our missing constant from an equation that will make the function differentiable. And that is our target for today. Our target is to determine the missing value of a constant that will make a function differentiable. What I'd like to do is actually start by reviewing the connection between differentiability and continuity. And the reason I want to go over this again is this is a hard idea. There's a lot going on here. And so I wanted to show you some examples that I think will help you kind of understand this connection. So as a review, if a function is differentiable, it has to also be continuous. However, just because a function is continuous does not necessarily mean that it's differentiable. So there are times when a function is continuous, which means connected, like at a corner, a cusp, or a vertical tangent line, but the derivative does not exist there. However, if the derivative exists, you have to also have a function that's continuous because not being continuous disqualifies it from being differentiable. Okay. Considering the following piecewise functions, you're going to notice that there are three piecewise functions here. They all have the same breaking point at x equals 1, and they're very similar functions, each of them. However, we're going to be looking at these three because they all have something a little bit different going on when it comes to continuity and differentiability. So for part A, for each of these functions, we're going to be trying to determine if that function is continuous at x equals 1. So in order to determine whether a function is continuous, we need to look at the limit as x approaches 1 from the left. We need to look at the limit as x approaches 1 from the right. And we need to look at f of 1. So if I do that, I'm going to plug the 1 into the top to the left, which is going to give me 2 minus 1, which is 1. Plug the number 1 into the bottom to do the right, which is 0. And the equals 2 is on the bottom, so that would be 0. Since 1 does not equal 0, this function is not continuous at x equals 1. And because it's not continuous, it's automatically not differentiable. Now, if we look at the graph, which I've already created here for you, it should make sense when you look at this graph that this function is not differentiable because there's a jump there, and it's also not continuous because there's a jump. And it makes sense that there's a jump because the limits on the left and the right don't match, so they're not approaching the same value. So that's one possibility. We can have a function that is not continuous, which automatically means we're not differentiable. The next possibility we're going to look at is for this next equation, it's a slightly different equation. So let's see how that changes things. The limit as x approaches 1 from the left, the limit as x approaches 1 from the right, and then f of 1. All right, to check the left side, I would use the top equation here, and when I plug it in, I get 0. To check the right side, I plug it into the bottom, and I get 0. And then the equal to is also on the bottom, so I get 0. So yes, this function is continuous at x equals 1. Now, once you're continuous, that does not necessarily automatically guarantee that you're differentiable. So in order to check whether this function is differentiable or not, we're going to need to actually find the derivative. So the derivative here of this piecewise function would be, if we do them one at a time, negative 2 on the top and 2x on the bottom. I'm going to put the x is less than 1 and the x is greater than 1, but I'm not going to fill in the equal to because I don't know if the derivative exists at that breaking point or not, and I don't want to fill that in prematurely. If I want to check to see if I'm differentiable, if I plug the 1 into the top, I get negative 2, and if I plug the 1 into the bottom, is 2. Since these two values are not the same, that means there's a sharp change in the slope. So this is not differentiable. Now, I would say that this is a corner because there's a sharp change in the slope at that value. If we look at the graph, we can confirm that. This is a graph that is continuous. It's connected, but there's a sharp change in the slope, and so there's a corner in the graph, which means the derivative does not exist. Last but not least, let's look at a slightly different piecewise function again. So we can check to see whether this function is continuous by looking at the limit as x approaches 1 from the left and the limit as x approaches 1 from the right and f of 1 and seeing if we get the same value. To check the left, I would plug the 1 into the top and I get 0. The right, I would plug the 1 into the bottom and I get 0. And then the equal to is also on the bottom, and those are all the same, which means this is a continuous function. Since this function is continuous, we can now check to see if it's differentiable, which means we're going to need to actually find the derivative. So f prime of x would be, I'm going to take the derivative one piece at a time, 2 on the top, 2x on the bottom. I'm going to put the x is less than 1 and the x is greater than 1, but I'm not going to fill in the equal to yet because I'm not sure if it's differentiable there or not. If I check the limit as x approaches 1 from the left of the derivative function now, I get 2 because that's the top. And if I check the limit as x approaches 1 from the right of the derivative function, I get 2 because that's the bottom. Since these are the same, this function is differentiable. So even though there are two pieces, they're connected in a way that the slope has a nice smooth transition, which we can confirm by looking at the graph. Even though this is a straight line and this is a squared, so it's a curve, they connect in a nice smooth way. There's no sharp corners, which means the function is differentiable. Hopefully this helps to clarify the connection between differentiability and continuity and to really see there are several different possibilities here. Next, we're going to look at fixing a function to make it differentiable. Every piecewise function has the potential to be discontinuous at the breaking point. Even if a piecewise function is continuous, it's still possible that there's a corner, which means it's not going to be differentiable. So we can determine the values that are missing for numbers in a piecewise function that will force the function to be differentiable by considering both continuity and differentiability. So let's take a look at this. Consider this function. We've got a missing value c and we've got a missing value d in this equation. First, we're going to use the limit definition of continuity to determine what we need to do to make the function continuous at the breaking point. So continuity says that we need the limit as x approaches 2 from the left to be equal to the limit as x approaches 2 from the right, which needs to be equal to f of 2. So the left side would be the top, so I would have 2c plus d. The right side would be the bottom, so I would have 4 minus 2c. And the equal to would be the top again, so I'm not going to write that down again. But this is kind of equation number 1 that we're working with here. 2c plus d has to be equal to 4 minus 2c. Next, we need to find the derivative and analyze it to determine if the slope is the same on both sides, so of the breaking point. And I spelled this wrong. I apologize. This should be breaking, B-R-E-A-K-I-N-G, not breaking like breaking a car. So in this case, let's find the derivative. So my derivative equation I can find by just taking the derivative one piece at a time. On the top, the derivative would just be c, because the derivative of c times x would just be c, and then the derivative of a number would be 0. And on the bottom, the derivative would be 2x minus c, because the derivative of x squared is 2x, and the derivative of negative cx is minus c. I'm going to put the x is less than 2 here, and I'm going to put the x is greater than 2 here. But I'm not going to fill in the equal to because I don't know if it's differentiable yet. Now I'm going to check the limit as x approaches 2 from the left of f prime of the derivative, and I'm going to check the limit as x approaches 2 from the right of the derivative. So just like I want the function to be continuous, I want the derivative to be continuous. So if I plug the number 2 into the top, I'm just going to get c, And if I plug the number 2 into the bottom, I'm going to get 4 minus c. So this is my second equation that I'm going to solve in order to solve this problem. Now, to actually solve for your missing values, you're going to need both of these equations to figure out both c and d. The first equation here has a c and a d, so I can't solve that yet. The second equation has a c and another c, so I can solve that. So if I start with the second equation, I can solve this by adding c to the other side and then dividing by 2, so c equals 2. Then I can substitute that value into this top equation, which means I get 4 plus d equals 4 minus 4. And now I can solve for d. So 4 plus d equals 0. And if I subtract 4, I get d equals negative 4. So if we use the values 2 and negative 4, I'm going to have a continuous and differentiable function. Okay, that is it for today. Thank you guys so much for watching, and I will see you for some practice in class.